Okay, let's look at some 2D logistic regression examples. Here is some data set. This is just a quick example. Here's the data set. Let me run it. And let's now plot it. And it looks like within perhaps some elliptical region. So the inputs are sigma x, sigma y. Let me actually clear all first. Let me load data set here. And we have three variables, sigma x, sigma y, and then y. Y is actually called a logical variable because it's just zeros and ones. Or you can convert it into real numbers, zeros and ones, doesn't matter. Okay, so y list, zeros and ones, sigma x list, some real numbers. Okay, so what we are doing here is basically we are plotting sigma x versus sigma y in the data set, and when y equals 1, we are plotting that with red crosses, and then when y equals 0, we are plotting that with blue circles, like so. We can also plot this in 3D. So let me plot this thing in 3D. This is actually a 2D plot, so I should probably plot it in 3D in some manner. So let me plot it. And then the actual, we don't have to, let me just plot it with black dots or something. And let me run this piece. It says blah, blah, blah. Okay, I'm using two-dimensional plotting command for a 3D plot. So let's fix that. Plot 3 is what you use. Okay, so that's what that looks like. Sigma x, sigma y. Now, of course, it's the 3D plot, so we can get to turn it. Okay, so that looks more like it, right? So recall that we have this. So the value of y is 0 for a small elliptical region and then 1 elsewhere. Okay. Now we want to now find a function that somehow naturally classifies this data, or we are trying to find this decision boundary, right? Which, like we said, is probably going to be elliptical. Okay, let me close these things. So the procedure is basically the same as before. All that changes is this X matrix and B matrix. Because now we want to approximate something elliptical, we have a list of ones for the constant term. We have sigma x, sigma x square, sigma y square, sigma x, sigma y. So we have all the quadratic terms. And it turns out that if you have all the quadratic terms, you should be able to approximate an ellipse, a hyperbola, etc., etc. And then because we have 1, 2, 3, 4, 5, 6 terms, we need to have 6 unknowns for B, B naught, B1 till B5 or whatever. Let me just make them all zeros. This works sort of best, I think, with initial conditions equal to zeros. Okay, and then this just is defining your options for the optimization. And this is actually exactly the same as before. The logistic class function, we are trying to minimize it. So everything is basically the same except the data is different. And then this X matrix and B input are different. B input is barely different. All that we have done is added additional unknowns. And then X matrix, we just added additional columns depending on what expression that we want to approximate. Okay, so let me run this whole thing step by step. We already saw these pieces. Run this, options. This is the fmin nunc optimization. We can see how long it takes. Okay, so it took 68 iterations. It called the function 476 times, so lots of times, and it reduced the function. It started out with the function value equals 0.693. It reduced the function all the way to basically 10 power minus 6. So it's gotten a very good, well, it's a positive function and it's super small, 10 power minus 6. So it's very good. And then it's gotten values for B result, which are these quantities. Okay, so now let's say we want to visualize this. How do we visualize the surface that we've constructed? The surface we've constructed is basically let me first do this thing. First, it'd be nice to actually draw an ellipse in this plot to actually show, hey, here's the ellipse that actually separates those things. Okay, so if you say, what is it called? B result. Those are the values of the coefficients. So let me just show something here, figure 5 or something. If you want to plot something like an ellipse or a circle, you can do something like this: 3 times x minus 4. Let me just make something up here. 3 plus 4 plus 3 times x plus 4 times y plus 5 times x squared plus 6 times y squared plus, I don't know, minus 2 times x times y. Okay, I say easy plot that thing. Nothing happens. Let me actually, unfortunately, nothing happens here, but because it's outside the boundary, I think. Okay, there we go. So you got a little ellipse there. So this expression setting equal to, so basically easy plot takes this expression, sets it equal to 0, and tries to essentially plot the set of all points where this is equal to 0. So that's, so if your separating boundary is of this form, you can just go easy plot that expression and you'll get the ellipse. Okay, I can just say hold on. I guess it's the same one or something. Okay, you see various ellipses there, hopefully. Okay, in any case, so that's a way using easy plot, you can actually plot these separating boundaries. So that's what we are doing here. I'm actually using a sort of a shortcut. So how do you say something like this when all you know are these coefficients? What I'm doing here is actually assembling this text piece by piece, character by character, using the numbers in B result and then using easy plot on it. So let's briefly look at how that works. So I'm going to say figure 1, I'm going to plot it in figure 1. And then I define these text characters or pieces of strings, and then I define temp as number to string B result of 1. So I take B result of 1, namely this thing, and then convert it into a string. And then I say, I go through I equals 1 to number of terms here, and say initially it's basically B result of 1. And then let me put a pause here and let me uncomment this thing. What will happen here is basically the temp is a string and it will acquire more terms as we run through this loop. So let me run this thing. So temp initially is the string minus 1492, which is b result of 1. And then after the first loop, it becomes minus 4292 plus x times, this is x, this is times, and then b result of 2, which is 154. And then when I press enter again, the next term will get appended and so on. Okay. So I'm just assembling this string piece by piece. And then once I've assembled the string, I just go easy plot of that string which is contained in temp, and notice that it produced this very nice ellipse that just separates very nicely these points and these points. Okay, so what did we do? We essentially had all these inputs basically decided on a quadratic expression, found the coefficients of that quadratic expression, and then now we can plot the separation boundary for this quadratic expression. Okay, and then we can do a surface with this as well with exactly the same expression. So okay, so that's the easy surf version of it. There is a command called easy surf that works as well. Okay, so the function, the logistic function, when operated on this quadratic expression, becomes 1 just inside the ellipse and becomes 0, close to 0 outside the ellipse. So if you use the logistic function with this quadratic expression, given a value of sigma x and sigma y, you can predict whether the material, let's say, will fail or not, right? So what is the purpose of doing all this? Is to basically get this g of sigma, g of z, which is h of sigma x and sigma y, which is this function, right? What does this function do? Just to recap, if you give someone a value of sigma x and sigma y, you can compute this quantity, this expression. You evaluate the quadratic expression and then put that quadratic expression inside g. So it's g of that quadratic expression, and it will give you a value either 0 or 1 or something in between, and that'll tell you sort of a probability of whether the material will fail given sigma x and sigma y. Okay, so that's sort of what we started out to do, to build a predictive model based on data that looks like this. Okay, so that's 2 inputs, 1 output logistic regression. If you have 3 inputs, 4 inputs, 200 inputs, exactly the same. The only things you need to change, literally nothing changes. The only thing that needs to change is the number of terms here increases, and therefore the number of unknown coefficients increases. And of course, if you have many more dimensions, you will not be able to plot anything meaningfully, so forget plotting. But you will still have this expression which can tell you in a new circumstance whether the material will fail or not, or if it's a different decision or a different classification, like what class a new object will belong to. Okay. So the next few videos, we will use essentially the exact same code. We'll barely change anything, but use this to do character recognition, right? So given an image, can you tell whether the image contains a 0 or a 1 or a 2 or what number? And then we'll use the same method for differentiating between maybe cats and dogs or something.